Um, so it's my pleasure today to be able to open the ComfDemo dissemination event. Just to give you an introduction, ComfDemo is a project that has been performed under the European Union's Clean Sky 2 joint undertaking, which means it's a research project funded by the European Union. My name is Victor Norefeld. I work at Fraunhofer. So Fraunhofer suggested this research topic to be published by the European Union. ComfDemo successfully applied to it, where we are really happy for that we got such good partners. I had the honor to be the topic manager and to follow this project from the start to today's results presentation. And my role was to make the link between the European Union, the other project partners, and the ComfDemo consortium. Just to give you an idea where the ComfDemo project or in which frame it goes in, we are actually doing research on tomorrow's regional aircraft. What we have seen in the past years is that many turboprop airplanes have consecutively been replaced by small jet-driven aircrafts. One of the reasons is increased noise requirements. However, what we know is that open rotor aircrafts often are more fuel efficient. And this is why now with increasing energy prices, of course, this concept comes back into focus again. Therefore, we are really happy that we had ComfDemo on board because ComfDemo made really research on the entire range from passenger expectations to a turboprop aircraft, to the main comfort drivers of the aircraft, to a system, how we can replicate such a turboprop noise and vibration field in a mock-up, and an actual measurement campaign on a real turboprop. With this, ComfDemo really set out the baseline for the state-of-the-art comfort you can have in a turboprop aircraft. And I think that any development which consecutively comes in this sector really now has a benchmark set out by ComfDemo against which it can compare the new solutions. Therefore, I would like to give my thanks to the ComfDemo partners, my congratulations for the results you have achieved, and I wish all of you and us a very insightful and interesting results presentation now. So, well, thank you very much to the entire ComfDemo consortium from my side, and congratulations to you.
Thank you, Victor, for this nice introduction. I would like to share with you the topic factors influencing comfort, measured and modeled. But before doing that, we would like to have your opinion. So we will open the whiteboard. And the question here is, if you think about a turboprop aircraft, what are the factors that influence the comfort in a turboprop aircraft? And please complete that in the Microsoft whiteboard. And on the left side upwards, you see text. So you can click on the text and then you can write, what do you think is an important factor in the turboprop aircraft for comfort? So please write on the whiteboard. There's noise and vibration here. There's noisy. There is smell and temperature, noise, vibration, drone noise, living space. Whoa, a lot of things. But you see, in fact, many people look for noise. Thank you. We'll stop the whiteboard. We come back to another whiteboard later. And we will ask you what are the most important things you remember from the first part of this session, but that will be done later. Now I continue with the results we've shown in the literature and we measured ourselves. So my presentation is on, yes, wait. So my presentation is on aircraft interior priorities based on passengers' opinion. So in this case, it's really based on what passengers say themselves. It's not what we have measured. Later in the presentations, there are studies on what we measured. This ComfDemo project had in fact two important parts. It was making a digital twin of the human comfort, and it was the test protocol for a demonstrator. In Clean Sky, demonstrators will be made of future aircraft to test already what's happening in the future aircraft. So I share it with you. It's about passengers' opinion. So in this case, we did ask people to complete questionnaires in the aircraft while flying. And if you look at a study in the literature by Bowens, if you look at what are the most important factors for comfort in jet airplanes, you see that the seat anthropometrics, so how do you fit in the seat, is the most important factor. Noise is number 2. Smell and climate and vibrations after that. But we did also a real test in a turboprop flight on November the 3rd. It was a flight of 70 minutes, 2 times with passengers. Here you see the passengers going into the airplane. And what you see here, it's not the seat anthropometrics number 1, but you already knew it because we saw that on the whiteboard. Noise is number 1, so that's the most important factor influencing discomfort. And the second one is seat anthropometrics. The third is vibration, and then temperature and air quality. So for future airplanes, it's important to take that noise into account and reduce that noise. So I think it's important in the demonstrator, how can we test turboprop aircraft with less noise. If you look at the seat itself, what has priority in the seat? Nijholt did a large study where you asked people that were sitting in an aircraft seat. And then number 1, which was mentioned, is legroom. I don't think that's a big surprise to you. Number 2 is the cushion, the hardness of the cushion. Number 3 is the lumbar support. Number 4 is the seat width. Number 5 is recline. By the way, it's interesting that many people like the recline, but the persons sitting behind, they don't like the recline. And then you have the headrest, the armrest, and the footrest. There's also a nice study done by Anjani, and she compared if you change the seat pitch, so you have seats a little bit wider from each other, and you compare it with the width, so that's a wider seat. What is the effect on comfort? Well, here you see the effect. If you, for instance, have a 30-inch pitch and a 17-inch wide seat, and you change that in a 30-inch pitch but a 18-inch wide, you see the comfort increases. And if you compare the 30-inch wide 17-inch and you make the pitch larger, you see it also increases, but not so much as the width. So if you try to improve the comfort of the seat, maybe look first in the width and then in the seat pitch change. Here you see a person which sits in a smaller aircraft seat, and you see it's the width is an issue, and it's especially for the shoulders an issue. Many studies show that hip width is dependent. Hip width is influencing the seat width. But if you have an 18-inch wide seat, which you see on top of the slide, and you compare that with the hip breadth, well, 95%, the P95, they all fit in there. But if you look at the shoulder width, the males don't fit in there. And if you look at the elbow width, the P95 female and P95 male don't fit in there as well. So maybe it's more important to look at the elbow width if you want to create comfort than at the hip breadth. So in summary, I shared with you that propeller aircraft have potential. That was already mentioned by Victor. They are more sustainable because they have less fuel consumption and so less CO2 they make. And in ComfDemo, we make a digital model and a protocol for the test. And for the protocol, attention is needed for noise, seat dimensions, vibration. And this is relevant for future propeller airplanes. Then I give the floor to my colleague, Professor Herbig.
Thank you, Peter. And I'm now presenting you some more in-depth results on our in-flight questionnaire campaign. And as you already heard, we did a lot of questionnaires in this 2 flights to and from Rotterdam. And just to give you a short impression, we had 70 minutes to do a really comprehensive analysis of the comfort people experienced. So what we did is we tried to measure rather important points like noise and vibration for different flight phases, and other things that we thought wasn't too important, for example, light, just one time during the flight. So we had to align this with the flight sequence, and the sample we had was 94 participants, more men than women. That was a bit sad. We have the people that are a bit on the young side with an average BMI. Half of our participants were experienced in traveling in the turboprop aircraft, and the majority of the participants, of course, indicated a positive attitude towards flying. That is rather important because we don't usually get people in the aircraft that don't like flying. Just coming to the first result, for 4 times we asked people their overall discomfort and their overall comfort. And you can see here that from 1 to 10, people had to indicate how discomfortable and how comfortable it was. The overall comfort is rather high, around 6 to 7 on a 10-point scale, and had a small decrease over time from ascent to taxiing, whereas discomfort had a small increase over time, but was in general rather low at about 3 points on this 10-point scale. In more detail, if you look at different environmental parameters, you see that we have and here the ratings are really on the average as for comfort as well as for discomfort. That is, participants have a decreasing noise discomfort rating over time and an increasing comfort rating over time, but it's still rather in the middle. Now, please don't worry, I'm not going to go into any detail on these numbers. But what I want to show you is how this develops. These are association, and the association is across bodily sensations. That is the local body part discomfort and the local experienced vibration. And this is really going to influence the vibration, comfort and discomfort, and the acoustic comfort and discomfort. And what you do see over time is that this is the associations are getting stronger and more, and this is even cumulative to the last measurement during descent. And what's interesting is also that we do see this on a very, very low level. People didn't experience much local body part discomfort or local vibration, but it still has a rather increasing and cumulative effect on the comfort and vibration situation. This is already shown by Peter. These are the important factors people had to report over time, and these are noise, vibration, and seat that are the most important over all measurement times. Noise decreases as importance for discomfort, whereas seat increases as an important factor for discomfort. And if we do this in a cluster analysis, we see that we do have 3 clusters of important factors for discomfort, and this is one that says noise, vibration, and seat is a very most important thing. The second biggest cluster is temperature and noise as the most important thing, and temperature and seat is a smaller cluster. What's interesting is that people with higher experience in flying, regardless if it's turboprop or jet aircraft, report more of the second cluster, that is noise, vibration, and seat as discomfort, than do people with temperature and noise as a cluster. So there is an experience factor, and we also have a noise sensitivity factor, that the people in the temperature and noise cluster are the ones less sensitive than the one with noise, vibration, and seat. Last result that is, I think, rather important. We asked in the very end of the flight, would you fly again with a turboprop? 80 people said yes. That is a very, we would do that again. So a very high number of people, but we have 11 who said no. And these differ systematically across several things. And the most important you can see here is the acoustic environment, but even more so and more reliable so, it's the vibration they experience during the flight. That's much higher for the people who say we won't fly again with this aircraft type, and the ones who report a lot of more local vibration on their body. So we have this vibration part as important. All other aspects didn't play a role in the decision to fly again. So to sum up, most people felt rather comfortable. The data are really good, and a lot of people would fly again. Noise, vibration, and seat are the most dominant discomfort factors. They are also the ones discriminating between the different participants who would fly again with turboprop and who would not. And the development of comfort and discomfort experience over bodily sensation seems to be rather complex. And that is definitely a problem and a challenge for the modeling we will do in ComfDemo, and we did already in ComfDemo. And that is something my colleague is going to tell you something about. Thank you very much.
And hello, everyone. And my name is Wolf Song, and I will take a short presentation on digital twin of comfort. That's our first attempt in modeling passengers' comfort experience. And just before me, two professors talked about subjective view of passengers towards different factors of comfort. And the construct of comfort is rather complicated. Like Professor Neil Mansfield said, and product itself can never be comfortable. Actually, the user decides, and it's comfortable or leads to discomfort by using the product, and even over time. That means comfort is personal, depending on our background, and comfort is multifactorial. Not necessarily one factor make extreme comfort means the person will be comfort. So for try to model comfort, and we try to identify different factors, and here I show you our exploration of different factors, and not necessarily we go to all the details due to time limitations. And I quickly summarize those factors as local environmental factors. For instance, noise in the cabin. Macro environment, for instance, I sit close to who and product characteristics and interaction between human and product. And the human himself, he is positive person or negative person, and his flying experience. And the most important in between, I put a clock, and how about comfort over time? Can we make a model and link these objective factors towards humans' subjective feeling? That's what I want to explore in these 10 minutes. And we try to highlight measurable factors, and the approximate number is 32. I try to categorize them as time, local environment, macro environment, human, and product. And we see details, noise, CO2 level, humidity, temperature, light intensity, flying time, and which row you are sitting, which seat is window seat, L seat, or the flight schedule time. It's morning is pleasant or afternoon is more pleasant. And regarding human, and we see human have a little bit static factors regarding a flight. For instance, gender, age, you can't change your age within a flight. And the stature, how high you are, body mass, and the popliteal height, and the buttock, popliteal depth, and hip width. And also in between, I put a small cartoon, and we try to record humans' left-right shoulder movement and left and right waist movement. We see if we can record these 32 parameters and make correlations with the subjective feeling. And for this, we developed a measurement tool named Jacket. It's able to record the parameters which now in screen within the green rectangle. In detail, this Jacket it's a comfortable wearables. Inside, we put embedded systems which are able to record the parameters we just measured. We see a different movement, CO2, light, temperature, and the humidity. And in the left side, one of my PhD and wear one of this jacket. In total, we produced 20 of this jacket. And for this, we also select a representative population. And the mean age of these 40 people, we have 2 flights, morning 20, afternoon 20. The mean age is approximately 35, a little bit young. And the stature is average is 174. And we conduct this research in Netherlands. The average height is pretty high. And the body mass, approximately 74 kilograms. And the gender, we tried our best to balance, but we still have a little bit more males and then females. At the right side, you see 2 key anthropometric parameters regarding sitting comfort and about the quality of our population. And the popliteal height is the x-axis, horizontal axis, vertical axis is the hip width. We see our population, the 40 participants, and get a nice distribution among our general population, which is the circle and the blue point behind. And in the flight, and we put these 20 people into the seat positions, and we took 4 rows, 3, 7, 11, and 16. And in all C seat and close to L, and we try to arrange another a little bit, let me say, a little bit more higher density regarding this particular C direction. And we took morning and afternoon, we have the same configuration. And here I show you a recorded data example of CO2 levels. And you will see the green lines, you will also see the red lines. The green line indicates 20 participants in the morning. You see from the left, let's start to ride a bus to the airport. When they step out of the bus, then CO2 drops immediately to 400. Then when they step inside airplanes, because engine did not start it and high CO2 concentration, we can observe. Then during the flight and the engine works and the ventilation system works, CO2 a little bit back to normal. When they're landing, they step out of the airplane, CO2 dropped again. Then afternoon group take a bus, we will see a similar figure, same as morning when they take the bus. Those are the data, all 32 different parameters, we record them, and we try to make a first attempt towards a quantitative model. At the left is our input time, human, including movement, anthropometric measures, product, for instance, which is the row of the seat, microenvironment, for instance, CO2 level, local environment, for instance, noise level. The front is a little bit quiet, in the middle, somewhat close to row 8 and 9, the dBA perceived decibel is a little bit high, more than 80. At the right, and is the questionnaire, the answers of users' subjective feeling, and we are trying different modeling tools to link the objective data and with the questionnaires. And in our modeling, we take some hypotheses and we pre-processed our data. And here I just report in the first attempt, we try to model the changes of comfort and discomfort as the baseline differs per person. For instance, if I'm a negative guy, I always say comfort is 0, discomfort is 10 all the time. And maybe a positive lady will say comfort is always 8, 9, and discomfort is always 2 or 3. At this moment, and we try to suppress this effect by modeling changes of comfort and discomfort. And we took 60 seconds as the basic time unit. And we also augment or increase the amount of our data a little bit by linearly interpolate the comfort discomfort scores during this 70 minutes flight, because we can't ask user report every minute of their comfort and discomfort scores. And finally, it's data processing. We normalize all the data between 0 and 1, and minimum is 0 and maximum is 1. Try to make average weight of different parameters. And here I report our first attempt of the importance of factors regarding comfort and discomfort. At left side, you will see the importance of factors regarding comfort. Right is the importance of factors regarding discomfort. For comfort and discomfort, I listed the top 8. And for the comfort, we found at this moment a user hip width is the dominant factor, which row user seat is also an important factor because the row is closely associated with noise. And humidity also play a role, and the CO2 level also play a role. And we must acknowledge CO2 and humidity itself is closely associated with other factors. For instance, the smell of human, which is also a factor which Professor Peter Fink just talked in the user's subjective rating. And age also play a role in comfort. Then it's time, temperature, then it's window or aisle seat. That's regarding comfort. For discomfort, we see the top factor actually is the window and aisle seat. The second one is a time. Let's clearly see the discomfort develop over time. Then row, humidity, noise, and the temperature, hip width, and age. For comfort and discomfort, now we highlight 8 factors, and these 8 factors not necessarily be those factors individually are very important. Maybe some hidden factor associated with this factor are also important as well. And just make a quick summary. And this is a report of the preliminary result. And it shows we are able to make a step towards modeling human comfort experience using the jacket data and the local environment measurement. And we think anthropometry, seat position, time, humidity, CO2, temperature, and the noise are leading factors that influence comfort and discomfort. We have some limitations, and the noise and the vibration in microenvironment was not included yet. And another critical thing is in the Lubeck Air, the airplane which we rent is ATR 72-500. The seat pitch was a little bit luxury, it was 34-inch, which might influence the importance of other anthropometric measures because people now get very, very luxurious leg space. In the future, we will try to collect more data on different types of seat layout in airplanes. We will try to use different modeling tools with in-depth explanation of different factors. So thank you very much.
Now I'm going to ask you to think, you heard several presentations, 3 presentations, and think about what is important to remember, and you're going to put that on the whiteboard. The advantage is that you also see from others what they think. It's a base for maybe a quick discussion before the break. So we're going to show you the whiteboard again, and then you can write down what do you think is most important to remember from these presentations. Again, you can take the text on the left upper corner and then write it. There it comes. Whiteboard. I do. Yeah, there it comes. So again, on the left side, yeah, clean it. Just Yeah. And I'm looking at now. Oh, just make another error. Okay. So you can write down what is important to remember from the last dependence of the on experience with flight. Yeah, that's important. So indeed, we found out that people with more experience in flying rated different than people that have less experience in flying. Any other thing we should remember? People rate it higher or not? Vibration, noise, space, vibration, so that are important factors is mentioned here. Space.
It's more important than pitch.
Where is that written?
It's not wrong.
Oh, width is more important than pitch. Yeah, yeah, that's also good to remember. CO2, air quality, human smells, yeah. Improve vibration, seat and noise. Seats, time, legroom, seats, comfort, seats, rows, place, yes. Yeah, nice. There's also a question in the chat, so let's go to the questions and maybe see who can answer that. Oh dear. Let's go to the chat. Oh, this is not relevant. Here's a question. No. Oh, here's a question of Nick Gast. Did you consider cabin pressure as well? Or is that covered in overall comfort? That's a good question. We didn't consider cabin pressure, although we measured it. So, Victor, do you remember how? So at 17,000 feet, it was 900 hectopascal. So that's comparable, by the way, at the place we are now. We are in Holzkirchen. But it wasn't mentioned in the questionnaire. And I wonder if people really feel pressure. So you have to find it out in another way. Then there's a question, did you choose the ATR intentionally, knowing that it's very loud? Or do you plan to repeat the same investigation in a quiet aircraft? Well, we did do this intentionally because we think future airplanes has to be lower in CO2. That means you get electrical airplanes with propellers, or you get turboprops, which also produce less CO2. So I think for the future, we should think more about propeller aircraft, and therefore knowledge in this field is useful, and therefore we did especially the study on a turboprop. In this case, we could find the ATR, and that's, yeah, if we could find a Dash 8 or a Saab 2000, we could have done the research with that, but it's now done with a Saab, with the ATR. Then the other question, some studies have shown that human emotions are heightened at 30k feet. If humans are more emotional at altitude, would that have had any impact on how they scored comfort in your study? Good question. Is anyone willing to answer that? Britta, can you come here?
Oh, okay.
Oh, you could have done it after,
Yeah.
you know.
Yeah, although I'm not familiar with this studies, we do know that there is some physiological changes at different pressures. However, I don't think that it impacts our results here, because all of our comfort and discomfort scoring exactly was done with different measurement times. So the individual changes over time would have been seen in the later measurements. For the pressure or the altitude, we didn't have too much altitude, so we can't say if this would happen, if we would see something at a very high altitude. So I'm not sure if we can say anything about it, but nevertheless, for our data, there is not an impact we have on the comfort or discomfort situation. And as turboprops are not really the ones going very high, we probably won't have this impact here.
Thank you. There are new questions, I see. SAP 2000 is a turboprop, yeah, we know. Were there differences between the flights? How important are comfort experience of the pre-flight phase? Were the difference between the flights? Yes, there were differences between the flights, especially the early morning flight. The airplane was cold in the beginning, so that means the temperature was experienced there as low. And what was also interesting is in that case, the temperature at the feet stayed rather low, around 17, 18 degrees, and at the head it became during the flight 23 degrees. And for sleeping, we want warm feet and a cold head. And what we found out, and it's in many airplanes the case, that you have cold feet and a warm head. But thank you for the questions. We now have a short break, and use that break for walking through or do something different, because your comfort is important for us as well. A webinar, it's hard to concentrate for a longer time. So we have now a 10 minutes break. So we ask you to come back at 3 o'clock. So go to the bathroom, have a coffee, walk a bit, and don't stay seated. And then we'll come back at 3 o'clock. Thank you for your attention. Welcome back in the webinar. There are some questions not answered. We will do that at the end of the session at the discussion time. So now the floor is for Michael Bellman.
Good afternoon. My name is Michael Bellman, and I will present. It works? No, it doesn't work. Good. And I will present the main results from the in-flight measurements regarding noise and vibration inside the cabin. So we had the possibility to perform measurements during 3 flights. The first 2 was including PECs, and the other one was without PECs, so only the experimental persons are involved. We are measuring in the RTR 70 to 500. And we had 2 permanent measurement positions of noise and vibration. It's in row 2 and in row 15 for the first 2 flights. And for the 3rd flight, we also added the row number 9. You could easily see it here. And we have the possibility during the 3rd flight to make some additional spot measurements regarding noise and vibration. So not only for sitting PECs, but also for flight attendants in the A, and as well as in the galley and toilet, and so on. So we do not have data from only one sensor, so everything was fine and well recorded. And I'm just want to say thanks to Lübeck Air, who support us by undertaking this experiment. So we, for the first 2 flights, we measured continuously from taxiing to taxiing with microphones in a sitting position of the PECs in seat row number 2 and 15. We have 16 PECs included in both flights. And you could see here, it is in, let me say, in the height of a sitting person. For the 3rd flight, we also be able to add more measurements, and there was a restriction So it was due to safety restriction not allowed to make additional measurements in the first 2 flights. That's the reason why we have this flight without PECs. So we could measure not only at let me say where the persons are sitting, but also in the galley as well as in the air. And what you could see here is on the x-axis, you see the time scale. On the y-axis, you see the measured sound pressure level, unweighted. And for sure, you could see the different flight phase. So from taxiing to taxiing, you see it's very noisy when you have takeoff and landing. And in between ascending and descending, you see something happened. And if you see from seat row number 2 until seat row number 15, something happened. So we have differences in between different seat rows, but we also see that the level is not constant between ascending and descending. So we have to analyze what could be the influencing factors on that. And this is why we have a bit more detailed look on the results. Here you could also see the sound pressure level on the Y scale, and the X scale you see the time scale. You see flight number 1 and 2 are very comparable regarding noise. So you see the upper graphs in red and blue, it's the unweighted sound pressure level, and the lines below, it's the red and blue. It's also in row number 2 and 15, the A-weighted levels. And you could also see that the third flight, where we do not have any PECs inside, the temporal shape of these recordings will be significantly different for the unweighted SPL, but for the weighted SPL, so A SPL, it's very comparable. And so what we found out is that for the unweighted SPL, we found similar levels in the first flight with PECs. And during cruising, we see higher levels for the row number 15, which is in the back, compared to row number 2. And we see that flight number 3, we have similar SPL in row number 2 and 15. So it might be the influencing factor PECs is inside or not inside. For the A-weighted sound pressure level, we identified that we have slightly reduced the level differences between row number 2 and 15, so in the back and the front. And we also see that row number 15 was lower levels during the third flight. So question is now, what are the influencing factors on noise? Are these the PECs or altitude or speed or something else? That's the reason why we plotted our measurement data from the third flight at different locations, measured at different locations, compared to the altitude and the speed. And you could clearly see that there is a high correlation between the noise level measured at different positions in the cabin with the speed as well as with the altitude. So especially there is a significant dependency on row number 9 and row number 15 compared to the altitude and to the speed. If we now have to look more into detail in the frequency spectrum, so on the left, on the Y scale, you see the sound pressure level in 1/3 tape step, and on the X scale, you see the center frequencies. Then you could see for the unweighted, we have a strong tonal component. This is the blade rotor frequency around 1 Hertz. We see that we have a lot of low frequencies, so it's not surprisingly. But we also see that in the region between 1 kHz and 2 kHz, where speech take place, we have a lot of differences and a lot of noise inside, especially if you're sitting in the front of the cabin. And we see also a trend, high noise amplitudes occurred, especially for high frequencies at row number 15. We also make some spot measurements in row number 6 and 8 for walking persons, so for flight attendants, and you could clearly see that we have differences in the unweighted sound pressure level if we are going from the front to the back, as well going to the galley. So the galley was extremely silent compared to other galleys we measured in previous projects. And if you are going to the toilet, you could be a little bit feared, because if you close the door or if you press the flush button, it comes a lot of noise to you. So you don't have to be scared for that. If we have a little bit more detailed look into the results, we could compare, let me say, the frequency spectrum. You could see it on the bottom, and you could see the overall broadband levels, A-weighted and unweighted. And what you could clearly see is that the frequency spectrum changed significantly if you are sitting in the front, or if you are sitting in the back, or if you are staying or in the galley. And you could see if you are very close to the rotor blades, you see the dominant frequency, rotor blade frequency at around 100 Hertz. You also see what happened on the perceived, on the perceptual side, if you compare, let me say, the SPL and the A-weighted SPL. So a lot of things happened in the frequency range between 1 kilohertz and 4 kilohertz. So there where speech is taking place. We also make measurements of the vibrations only for the third flight. You could also see that we are starting from texting to texting. We also see that we have differences if you are measuring in the middle or in the back of the cabin, and for sure if you are measuring in different directions. What we also see that for sure the dominant frequency component is 100 Hertz, but we also observe that we have a lot of frequencies or a lot of energy in frequencies between 100 Hertz and 500 Hertz. So we measured the frequencies or measured the vibration up to 1 kilohertz. So there is a strong indicator that if you want to have an objective description of the subjective perception of vibration, that you have to enhance the ISO standard to higher frequencies, because a lot of things happen between 100 Hertz and 300 Hertz. So I come to the end of my talk. We present that we have met continuous noise and vibration measurements during 3 flights with and without PECs in an RTR 72500. The noise and vibration significantly depending on a flight phase, which is not surprisingly, between taxiing, takeoff, and so on, in level, but also in spectrum, which is highly correlated to the altitude as well as with the flight speed. Noise and vibration significantly depending on the location where you're sitting or standing or working, especially for the cruising condition. And what we also observed is that the sound pressure level is dominated by the rotor frequency and by very low frequencies, but a lot of things also happened when you're looking to the ASPL, so the A-weighted sound pressure level in the frequency range where speech take place. For an objective description of the subjective perception of noise and vibration, we do definitely need psychoacoustic metrics, and we are working on this. And for sure, there is a hint, that noise, maybe also vibration, might also depending on the amount of PECs, so how many PECs are inside the cabin. So for Outlook, we have now vibroacoustic recordings which we could replace or reproduce in cabin simulator and could change, let me say, one of these 2 metrics. And we are currently also working for future psychoacoustic analysis. And what we want to do is that we have an objective description of the subjective comfort and discomfort perception. Thank you very much.
Okay, so I'm Neil Mansfield, and I'm going to be presenting to you some studies that we've done at Nottingham Trent as part of the project, and some of this is some laboratory work that we have been carrying out. So what I'm going to talk to you over the next 10 minutes is about our goal of understanding how passengers integrate comfort and discomfort factors into their overall experience, and the 3 approaches that we had to this. So to begin with, we wanted to complete a voice of the customer survey. And then COVID hit us, and so we had to do it in a different type of way. But what we did as the way that we elicited our data was we ran some focus groups with different participants of different ages. And what we were trying to do there is to understand the opinions of aircraft, different types of aircraft, and their experiences. We then take that data, transcribe it, and we can do some analysis on what people said in those studies. And to summarize, what we found was the topics that people spoke about changed a little bit between groups, but the most important areas that we discussed, the things that are in our control as maybe aircraft designers or operators, are people like to talk about space. They were talking about noise and air quality. They talked about vibration, and particularly older groups talked about the thermal environment. there are other things that were discussed, but perhaps outside of the scope of our focus here. So, for example, hygiene. This was in the middle of COVID, and perhaps entertainment, for example, so other areas which are outside of the fundamental design. So what this has done is this has confirmed that what was in the literature before, but this time focusing it on turboprop and jet aircraft, that we were still in the right area. So then the question is, what happens when people are exposed to these multiple stresses of, let's say, noise and vibration and thermal vision? And the three ways that we could see an interaction, which would be perhaps an additive interaction, where if you have two stresses, you have one, you have a second, and you add them together as to give you your overall combined impact. Maybe we'd have a cross-modal effect. So, for example, if someone is exposed to high noise and high vibration together, maybe they'll be more critical of the vibration. So the presence, if we took the noise away, the vibration would, the sensitivity to that would change. So that's a cross-modal effect. The third one is kind of the opposite to that, which is a masking effect, where you have two stimuli and one of them actually reduces your sensation to the other one. All three of these there's literature to support that. So the way that we did it for this case was we looked at trials that were in a dual modality. So to start with, we looked at just noise and vibration. We were in the lab. We had a vibration plate that you can see on the image here. We exposed people to noise and vibration at the same time. And these were short samples. We had turboprop noise and we had turboprop vibration. These were synthesized, and each of them was about 15 seconds. And we had every combination of the vibration and the noise that you can see in the table here. So this means that we had every level of vibration tested against every level of noise and vice versa. So you can see all of these were tested. We then asked the participants, how do you feel about these? And they would give scores of the noise, scores of the vibration, and then an overall score. And this is a method that we've developed over several years of how to get good quality data collection. And the key thing with this is that we saw there's no surprise in the sense that as the noise goes up, noise discomfort goes up, or as vibration goes up, vibration discomfort goes up. So if we take that image on the left, the noise is on the axis, which goes kind of left to right on the right-hand side. The vibration kind of goes back into the screen, and then the overall is in the vertical direction. So what this is showing us, though, is that there isn't a cross-modal effect. The noise is the response. If you ask someone about noise, they give you a response about the noise. The same we saw for the vibration. If you ask someone about vibration, they will respond to the vibration. So this was really useful information for us in terms of developing our model. But then overall, we can see that there's an additive type of effect on the right-hand side. So the highest point on this surface is the furthest away point, and that corresponds to the highest vibration and the highest noise at the same time. The lowest position is the lowest vibration and the lowest noise. So this is showing that both of these factors are important to make conclusions about overall discomfort. If we sort of linearize these surfaces, then you can sort of see how they work with these squares. So then we moved on to our trimodal trials, and here we went into our environmental chamber where we can change the temperature, the humidity, and the oxygen level. In this case, we were only controlling the temperature. We had a similar type of protocol with the noise and the vibration, seeing every combination of each of those, but we ramped the temperature, so the temperature went up during the trials. In this case, we changed the scale slightly. The previous trial, we thought we wanted to extend it, so the noise and the vibration. And this time we also had a thermal factor. What was a unique part of this was we asked this question. In order to improve your comfort, would you prefer to reduce the noise, the vibration, to increase the temperature, or decrease the temperature? Now, first of all, in some ways, this was very similar to the previous study. We used slightly different questions and a different range of noise and vibration, but overall, they were. We had a similar type of surface. So I won't go into this again. I just showed you that for the first time we did this trial. However, what was really interesting for us in this case was what we saw about the preference. So if you remember, we had noise, vibration, and thermal. So what we did, we took the data and were able to map it. And what we in our analysis, we were saying, well, okay, if more than 50% of people say they prefer to reduce the vibration, we'll say that vibration is dominating. The same for reducing noise and the same for reducing temperature. And maybe you will remember that we could also ask people if they wanted to increase the temperature, but in this case, no one said that. But that's a bit of a flag here. This is not saying in the conclusions of this that the lower the temperature, the better. In this range, we already had a comfortable temperature at our lowest temperature. So at 20 degrees, then, you can see that depending on the noise and the vibration, that there is a map here. So if you have a low noise level but high vibration, people would like to reduce the vibration. The same story for the noise. If you have a high noise level, people would rather reduce the noise. And you can see that in this case, noise is dominant in most cases. However, for lower noise levels, the vibration can also be really important. The second element of this is that as we move up to 24 degrees, we have the second element on here. And you can see at the lowest noise and vibration, we say NP, that means no preference. None of the factors were above 50%. So this just shows that there is a range where there isn't much difference between the noise and the vibration. People are kind of in a sweet spot at that point. But you see a similar mapping to what we saw before. As we move up the temperatures again, you can now see if there's low noise, low vibration, but we're up at 28 degrees, the temperature starts to become important. And then, no surprises, but in this case here, you can see at 32 degrees, the temperature is dominant for the majority of the cases here. So what this allows us to do is to make some conclusions that if the noise level is above 86, then most of the time the noise is going to dominate over the vibration. But if we reduce the noise below that level, then the vibration becomes important as well. Similarly, if the temperature comes up, that will be dominating the response of our participants. So in terms of the takeaways for you, what we've done is we've looked at noise and vibration, then added in the thermal element here in a laboratory setting this time to help build our overall model that we'll see a little later on. No surprise that the vibration ratings increase with vibration or that the noise ratings increase with noise, but important that we didn't see any cross-modal effects in these cases in this study. Perhaps what was also reassuring for us is about the overall comfort. So all of the factors are important, but the modality, it does vary depending on the details of the environments and the modality for what people would like to change to improve the environment that they experience. And that's me finished.
So, hi, I'm Gerbera. I will shortly tell you something about small research we did parallel to the bigger ComfDemo research, or maybe actually following the bigger ComfDemo research. And this was about the impact of noise cancelling headphones on passenger comfort in turboprop aircraft. At one point we thought, okay, well, noise is a problem in turboprops, so how can we what can we do about this? And actually, already during the bigger ComfDemo test, one of the participants took out their noise cancellation headphones themselves and started, just use the headphones. And afterwards, I asked this person, okay, why did you take out the headphones? And the answer was something like, the noise was just very loud, so why wouldn't I? So following this, we just thought, okay, well, let's just test this and do something with it. Like we know, noise has quite an impact on the comfort experience, on the comfort and discomfort experience. And we also know that being in control of noise levels will already improve the aircraft seat comfort. So within this small test, we looked at the influence of noise cancellation headphones on the comfort of passengers, and we did a comparison of noise cancellation headphones and earplugs, and between turboprop sound and jet sound. Within this study, we included 24 participants between the age of 18 and 39, and with a 50-50 male-female group. And we asked them to do a relaxing activity, but preferably we didn't include sound. So we didn't add another sound source, but they were allowed to talk with each other. And we tested in groups of 4, each participant going through 4 conditions for 45 minutes. And we did this in an airplane fuselage on the campus in Delft, where we used the sound source from behind, simulating the aircraft sound experience. So one of the things that we started out, okay, this is going to be maybe a quite low, easy test to do, but then we found out actually that setting up the sound distribution was quite hard. So some of the things that actually came up is that when we played the jet engine sound, the noise distribution across the seats was quite different compared to the turboprop sound. So this led, because initially we included 6 participants in each test, but this led for us to exclude the outer seats because the turboprop sound reflected a lot against the walls, and there was no good noise distribution possible for test to make it the same as possible, which might sound quite logic, but it does show that if you are using the different sound in aircraft design, you might also want to look into the acoustic material properties of the different aircrafts. So looking at the overall preference, it's quite what we expected, but it clearly shows that noise cancellation headphones were preferred over earplugs, and that jet engine sound was preferred over turboprop. This was also represented actually in the comfort and discomfort comfort score, where clearly the noise the headphones score higher on comfort and lower on discomfort. So looking at this, you would say it's quite clear or that active noise cancellation headphones are preferred. But looking at some other questions, actually it's quite personal preference. So for instance, looking at this local body part discomfort, although the discomfort is quite low, ranging from 5 to 1, where 1 is a low discomfort and 5 is extreme discomfort. But it does show that, for instance, for earplug, the discomfort is a lot higher for the inner ear. And for the active noise cancellation headphones around the head, above the head or in the neck gives a lot of discomfort. And this also was represented in some comments from the participants saying, I don't want to wear the headphones, they give me headache, things like this. So comparing them a bit further, looking at blocking out noise performance, active noise cancellation headphones performed a lot better. But the earplugs, for instance, are a lot less heavy on the head, and they are quite easy to implement. But the active noise cancellation headphones, of course, have the option of including music, and they create, actually, if something extra we found out is that they create a feeling of privacy, which is quite a nice extra. But there is also a feeling of air pressure change. And some of the participants experienced a heightened awareness of vibrations and heartbeat, which they found very discomfortable. And for them led to saying, actually, they don't want anything on their head, but if they can choose, they would choose earplugs over headphones. Yes, and then finally, we also compared the simulated flight to the real flight, just to see how accurate our simulation was. And this showed a high similarity to the outcomes from the turboprop real flight. So as you can see, the noise actually scores is the #1 factor influencing discomfort, and followed by that vibration in the seat. This shows that for small, simple test, if you want to get an impression on acoustic comfort, this might be a way of testing it in a low-cost setting. So what are the main key takeaways? Well, active noise cancelling headphones are preferred over earplugs. The jet sound is preferred over turboprop sound. And for a low-cost setup for acoustic comfort related studies, this kind of setup can be used. And in material choice for interior, for instance, you might want to consider the acoustic, the acoustic qualities as well. So thank you, and now I would like to give the word to back to you.
Okay, thank you. So a lot of what we've been doing in the project has been with the goal of producing a model. And what we have done is we've created multiple models. Many of us have created different forms of models, based on the data that we've been able to obtain. So what I'm going to do is to cover some of the model details where we stand at the moment, but I have to say this isn't comprehensive, and it's not covering all of the models that have come out of the work so far and are still being worked on with the richness of the data that we have. So what I'm going to cover in the next 10 minutes is this aim, which is that what we'd like to do is to build a model or maybe several models of passenger experience of turboprop aircraft. That's the scope of what we have here. We're focusing on turboprops. That's where where our data's been collected. And we started with a baseline model at the beginning, and you've already had a little bit of a preview of that. I'm then going to expand that into what we have found in the studies that we've done. And then I'm going to take a slightly different approach of some numerical models that we have also developed from the lab testing specifically. So when we began the project, we pulled together multiple types of factors that could affect overall comfort and discomfort. So these ranged from, for example, the product properties and the environment that people find themselves in. Of course, these will interact. We then have the time that someone is being exposed to that environment, which is also another interaction. We then have those environmental parameters at any particular moment and how they interact with the sensory system. So those environmental parameters might be measured with a sound level meter or with some vibration measuring equipment. A couple of the images which I had to hand on here, but all of these different factors are integrated in by the human sensory system. Then these will affect the person's psychological state. There would also be an interaction with their physical characteristics, which something to do with the demographics or their anthropometry. That then gives them their current experience, and that will influence their comfort and discomfort. However, there could be triggers into other areas. And of course, some people are very experienced with flying. Some people are less experienced with flying. Some people, flying is part of work, is maybe mundane and everyday. Some people, flying is associated with going on holiday. So there are these other, the past experience is also very important. So kind of had this outline. And in fact, what we did with this is to turn it into, we strip out some of the images there, and we can turn it into this model where we kind of were at the beginning of the project. This was our starting point very early on, which included qualitative and quantitative factors. So continuing through the research, we've done some flight tests. So this is some of the details from the flight tests that we did about a year ago. We've done some lab tests, and there have been some tests that have been conducted in some cabin simulators in Nottingham and in Delft. And obviously part of, or maybe some of you are aware that the part of this whole project is designed to provide models that can be used in a cabin simulator. So we've drawn, what I'm trying to do in this presentation is to draw together some of the findings that we've discovered as we've gone through each of these different types of tests. So to begin with, I just want to give you a little bit of a key here. So there are multiple colors in this image. The green is things that we found during the flight tests. The orange color that's a dimension that was specifically looked at in lab tests, and the white are the passenger responses. And then we have some solid arrows that you will see, which are where we have data supporting the association, and the dashed lines are about some cross-flight phase effect. So that's just so that you can sort of see a bit of how this is going to work. So first of all, before people get onto the flight, they may have a negative mood, or they may have some positive past experience and a positive attitude. And through our flight tests, there was an association between the pre-boarding mood and the discomfort or the comfort during the first phase of the flight, the ascent discomfort or the ascent comfort. So your mood beforehand affects how you feel at the beginning of the flight. Another area that we looked at with our initial model was about the product properties, and some of the specifics were that where we found statistical links within the flight tests are if the seat is easy to adjust, then we have more comfort and less discomfort. The same for if there's a sense of space, and if there's restricted sitting, less comfort and more discomfort. So that was for our flight tests, which was an aircraft as it is. There wasn't like a systematic keep on changing, so you would need to look elsewhere and to where there is other research which has looked at this systematically with adjusting, for example, the sense of space. What else did we find? Well, as time went on, as you progressed through the flight phases and time, of course, we can't separate them out. We can't have a flight where the descent happens before the ascent, so you can't separate them. But as you go through the flight, the body part discomfort increases over time. People feel stiffer, they feel worse at the end of the flight than they did at the beginning, according to the body part discomfort scores. And then we get into those physical and environmental parameters in the cabin. So we can link the noise acceptability, so the person's opinion of the noise acceptability, with more comfort, less discomfort. The vibration acceptability, the same, more comfort, less discomfort. The overall pleasantness, the same. The thermal acceptability early on links with more comfort at the end of the flight, and the air quality acceptability in the middle part of the flight also links with how people are feeling at the end of the flight. So when people deboard, their opinions at the end of the flight are linked to how they found it during the flight. So those were from the flight tests. From the lab tests, we can see that the noise level, so this is the objective measure of noise rather than the subjective measure of noise, which we had in the green above. The noise level does give more noise discomfort and more overall discomfort. And if the noise level is above, well, 86 dBA, as we measured in our studies, then it should be the priority. For vibration, again, the magnitude will associate with discomfort. Temperature, from our studies in our environmental chamber, around 30 degrees was where irrespective of the noise and the vibration, the temperature becomes the priority for passengers. So if we put all of these together, then we have multiple factors that we've looked at during the project with our experimental work in the flights and in the laboratory, and we can come to some conclusions as to what links with other items. And the things that aren't on here didn't have such a strong relationship based on the tests that we've done. But we're not quite at the end yet, because after, what's really important to us as people wanting to improve the environment of those who are flying is, would you consider flying in this type of aircraft again? And so what we found is that if we take the top dotted line here, the noise acceptability and the vibration acceptability, overall comfort on the descent and the overall pleasantness is a positive attribute to add to would you consider flying with this type of aircraft again. If there are some negative attributes, one of them being how many recent flights has the person had, so how experienced are they? The overall discomfort during the ascent and the descent, and the overall discomfort during the taxi. They're the negative attributes related to would you consider flying with this type of aircraft again. The other type of modelling that we've done based on our laboratory tests is modelling the overall discomfort and the individual modalities. So the top, we have noise, the bottom vibration, left is measured and right is modelled. So this is a fairly straightforward curve fitting task to produce an initial model here. But what we wanted to do was to expand this using polynomial functions and with multiple factors, which we did in MATLAB, and we then have produced a model. Well, how we can use this though is, and what we have here is actually a screenshot from a model that we have it actually runs in Excel. So we can type in the number for the noise, type in the number for the vibration, and it will give us a prediction of what the relative score would be for noise and vibration ratings at different temperatures. So this model here will give us a score based on the scale that I showed you earlier in an earlier presentation. Then for the overall discomfort, this is using these surfaces that we saw before. What we did is a machine learning method using a k-fold cross-validation, and this includes noise, vibration, and temperature as coefficients that we assume are linear. This method, it samples the data, we do it multiple times, but the key is we end up with actually an equation which is a little bit simpler than the one we had before. And what this will give us is we can have these parameters which will give us a prediction of what the overall comfort, or rather overall discomfort, is. I showed you this previously, and the other thing we brought into this model is predicting what the percentage of the percentage of people who would like to reduce vibration, noise, and temperature within a numerical model. So we end up with a second model based on the machine learning and the temperature, which will give us a prediction of the overall discomfort. So again, this is a screenshot from an Excel application using the model. So you type in the vibration magnitude, type in the noise level, and type in the temperature, and it will tell you, first of all, the number gives you the predicted overall discomfort score. It will give you the verbal anchor associated with that with the descriptor. So in this case, it will be moderate discomfort if we have 78 dB, a vibration magnitude of 2, and a temperature of 20. But this would say that we would expect that the passengers would say, I would prefer you to reduce vibration in this case. That's where we've got to with our modeling. So
bring up the whiteboard. Now we are asking you again from these last 4 presentations. What did you remember? And write it again on the whiteboard. What is important to remember for you? And then others can see also what might be important elements in the presentations. Take the text and write it down. And then we go to the questions in the chat. Let's see what comes up in the whiteboard. Let's see what comes up. Don't see any text yet. Oh, many factors for comfort. Yeah, if you look at the comfort models, it's really complex. It's not easy. But the first attempt was made. So you just type, go to the text and then you write. Temperature is a differentiator for comfort. Yeah. Especially high temperature has a big influence. Sound. Temperature effects for comfort. Sound pressure level. Comfort is a trade-off between factors. Yes, that's interesting. Yeah. Sound pressure level. Yeah. Comfort has a cumulative effect. Yes. If for instance, vibration and noise can add up, and even temperature can add up. Propeller signature. You can see the propeller signature in the sound. Yes, that was what Michael showed. And Many factors for comfort become more important with age. And comfort. Yeah. Okay. I don't think many new things come up. Let's go then to the questions in the chat. And I promised to come back to the question about the IFE. There was a question about IFE. Some studies have shown that human... No, that's not the wrong one. Well, there was a question about what IFE has an effect, and that was interesting. There have been some studies that with IFE or with a person next to you talking that can distract from discomfort. So there are studies where you feel the discomfort of the seat, and when you watch IFE or you play a game, you see that the discomfort drops. And that's the same for talking to your neighbor. You see that it distracts from discomfort. So IFE and having a nice neighbor can play a role. And then the next one I need to leave, okay, and then let's go down. There were questions. Why didn't you compare ANC headphones versus capsuled ear protection, which is quite differently perceived than plugs? Can you give an answer to that, Gerbera?
Yes, thank you. That's quite a good question. I assume that with capsuled headphones you mean the large headphones. So actually we did consider this as they're maybe comparable in comfort or wearability, but we wanted to create these two comfort options. Also considering factors like, for instance, the weight on the head. And for instance, with women, the effect it has on if their hair gets messed up or things like this. So that's why we wanted to compare these two options. And additionally, in previous research from Bowens, also earplugs were used. So that's why we also considered this.
And then you could compare it, yeah. And the Bowens showed that the fact that they have a headphone or an earplug already reduced the discomfort. So the fact that you have control of the situation when it's too loud and that you have possibility of doing something about it is already important. Then there was a question for predictive modeling using objective measures. What was used as the ground truth labels? Maybe Neil can answer this.
Okay, so for the predictive modeling, I think the term ground truth. So we use verbal anchors for the scale. So for the individual modalities, we based each of them on what's been published before and techniques that have been used before. So for the thermal scale was the ASHRAE scale. The first study we did was a shorter scale, but what we want which was just the noise and the vibration are what we would term our main study, had a longer scale because that then mapped onto what was done in the flight tests, but also it allowed people to give us more points. And so that went from one extreme rating to another. The overall discomfort scale, that one was based on, and it was an adapted Borg CR100 scale. It's a method we've used for over several years to build up this overall this scale. I'm going to try to. Here we go. So that's they won't see it. Maybe you see it now. Okay, so these were the scales that we used, and then these were the data that went into the models. So the no discomfort to extreme discomfort was the there. What you can't see on the camera is we have someone doing the magic with the laptop. Yeah. Here we go. Okay, so this is the ASHRAE scale and the noise and the vibration scales, and the one on the right is this CR100. So just to explain a little as to how this works. So the idea of this is that what we would sometimes call the priming questions, the A, B, and C on the left, are deliberately on a scale that does not map onto the scale onto the right, so that people don't then do calculations in their head to say, oh, I said a 7 and a 6, therefore I should give an average of 6.5. So it is kind of to try to stop that happening. So it's a completely different scale. The verbal anchors on there are designed. They've come. They actually came from. It's not fair to say that they are from the ISO standard, but perhaps they're inspired by the ISO 2631 has a scale for comfort. It has fewer points than this. So this is a hybrid of the verbal anchors on here. And the idea of this is it also goes above 100 on the scale, which allows people to kind of not have that ceiling effect. So they don't need to be frightened if they did go right up to this maximal. They could use 100 if they thought it was maximal, but they can see they can kind of burst through the top as well on the scale. Although in this situation, in these trials, of course, as you'd expect, no one got anywhere near that because of the type of environment that we were in. So that's where the data came from. So for the modelling, that this is what the numbers refer to. So they need to be referred back to these scales so we can have an understanding of what the numbers actually mean. So I hope that's answered your question.
Let's go to the next question. Predictive modeling we had. Okay, so this is the last one. Well, then we would like to thank you for your participation in this ComfDemo webinar, where we presented some of the first results of our project. And yeah, of course, there were some very interesting things presented, like for instance, that there is a difference between an empty flight and a flight with passengers, that there are many factors, that comfort modeling is not simple, but there are many things discussed. And thank you very much for your attention. And if you want to have more information about the project, go to the website www.comfdemo.com, and we'll also put this presentation on that website. Thank you for your attention.